I want to introduce the next speaker, that is my co-chair, Alberto. Is going to, here we're going to change. We are not going to talk about REM sleep disorder, but we're going to talk about EEG. And we're going to see, as you have the title of his talk. Thank you.
Thanks a lot for the introduction. And yes, my name is Alberto Jaramillo, as I have said before. And today we're going to talk now about resting state EEG, which is my topic. And we're going to focus on two different aspects of the resting state EEG, which are the oscillatory or rhythmic part and the non-rhythmic or aperiodic part of the resting state EEG. And we're going to discuss about the abnormalities that we can see in both features in different neurodegenerative diseases. And this is something that you have been, if you have been in ADPD 2025, this is something that I have been working since that time. And here we are updating the results with a larger cohort, quite larger. So hope you can find it interesting as well. Here is a QR code, so you can follow the presentation if you want to scan it and get it. And here are my disclosures. So first, I'm not gonna take too much time on this, but just to mention that the most robust feature of the resting state EEG that has been described since the beginning of the use of EEG in humans is the alpha rhythm, the posterior alpha rhythm particularly. And this is something that we can evoke in the participants when they close their eyes. And typically this rhythm has a frequency. It tends to have a pace between 8 to 11 cycles per second. So it moves around 8 to 10 hertz, let's say. But since the beginning of the use of EEG in humans, this is a picture of Hans Berger, the one that started with this. He realized that people with dementia senile in that moment of the history, they tend to show slower alpha rhythms. Here you can see an exemplary trace of a person with senile dementia in that time. And here is a very nice representation that I always like to use, because in the beginning we started counting peaks. Now we can get this done by the computer. So here on top you can see an animation of different brain rhythms at different frequencies, and here we can have a very easier way of interpreting this. Instead of counting 10 peaks, I can look at this and I can see that I have 10 hertz oscillations. But on top of these 10 hertz oscillations, I can also have 1 hertz oscillations or 20 hertz oscillations. And it's very difficult to count when you're just looking at the peaks. So when we do this frequency transformation, that's how we call this, we can realize about the frequency of the brain rhythms that we are looking at. And this is very interesting because this is the traditional spectral analysis that has been used for analyzing EEG. And in the context of neurodegenerative diseases, we have seen that both the oscillatory part of the EEG show differences in Parkinson's, Alzheimer's, dementia with Lewy bodies, and different neurodegenerative diseases, but also the non-rhythmic part, which is this slope that is below the peaks that we can see in the frequency component of the EEG. This slope, it's also affected, particularly in alpha-synucleins. It has been reported as very, very notably affected, as you can see here in this DLB example. And it can reflect both broadband neural firing and also inhibitory and excitatory abnormalities. So we have seen all this evidence, but is that evidence strong enough to say that we do have all these abnormalities in the EEG? Typically not, because most of the studies on EEG are performed on small sample sizes. But nowadays, with multicentric collaborations, we have realized that we can try to align the data to make it more comparable across different sites and pull more data sets. And we can do this by borrowing some methods from imaging, for example, COMBAT, as we have said before. And this is what I have presented on ADPD 2025. Here is a paper. It was not finished when I presented this. And this paper was performed on this sample, 11 sites, 8 countries, and it was done on what we call sensor space. And I'll introduce what is that now. because the objective for us is always to look at abnormalities in the EEG, because we want to use the EEG to separate the different clinical phenotypes, and also if we can in the future get biological differences between our groups, we want to get the EEG, make it able to separate the patients across these different phenotypes. But we don't want to have like a lot of side effects, batch effects. So in this case, we took data from more than 2,000 subjects. It's more than 16 sites, 13 countries. We try to represent the world as much as possible. But here, just to mention that we have a big outlier, a big cohort from Korea, that it's open. So if you work with EEG, please look at this name and you will definitely be interested in this cohort. So we have open data sets. We have data from the European Dementia with Lewy Bodies Consortium, which is the one that I'm mainly representing. And we have different phenotypes. We have from healthy controls, the Alzheimer's disease spectrum, the Parkinson's and Lewy body dementia spectrum, frontotemporal dementia, and vascular dementia. And basically, we pre-process our samples to try to get rid out of the noise in the EEG signals. Then we perform what we call source localization. And then we align our data to make it more comparable across all the sites. Then we perform this spectral parametrization, which is basically separating the rhythmic and non-rhythmic part of the EEG. And then we start comparing our groups. So we're going to talk about source localization. Before, we worked on sensor space, meaning on the electrodes. So we can get our frequency discomposition of these electrodes, and they look very similar. No matter if they are anterior, central, or posterior electrodes, they look quite similar. But when we are interested in the posterior alpha rhythm, we can say that this occipital electrode can receive sources from adjacent electrodes, such as the other side, the contralateral, or even frontal electrodes. And it can affect how this electrode will look like, how the signal of this electrode will look like. But fortunately, we can project our EEGs into a map, and then we can try to get our global representation of the brain rhythms, and then we can see more fine-grained aspects of the frequency. Here you can see that our alpha rhythm, which is posterior, it's very prominent in this occipital lobe that we created here from the DK Atlas. So basically, we took these source reconstructions of the frequency of the EEG, and we aligned them using combat, trying to keep the age and the diagnosis effects, because for us it's very important, but trying to taking out the side effects. And here are the sample characteristics. Here you can see that we do have a lot of variation in age, and that's why we want to align our data, but taking into account the effect of ages on this data, because age can also modulate the EEG rhythms. Here you can see an example of how the data aligns in sensor space and then in source space. And here you can see that overall in the statistics that we tested, both in sensor space and in source space, we observed that site-related differences are smaller when we compare across sites. The data looks more similar, but the diagnosis-related effects are almost the same. They are quite preserved between the non-harmonized and the harmonized data. And if you look at which frequencies are showing the differences, we can see that most of the differences are in this theta to alpha band, which is one of the most important for us. And here, I know this is a very, very busy figure, but I just want you to look at the boxes. So here we can see the Alzheimer's group. They are in blue lines, and you can see that both in the oscillatory part, the peaks, and the slopes, they show some differences with some of the groups, which I'm going to explain in detail in a while. And in purple, we do have the LBD group, which is the Lewy bodies dementia group, which they have been recognized as a group with a lot of EEG abnormalities. And you can see that these abnormalities happens in both the oscillatory and the aperiodic part of the EEG. And if we look particularly at descriptors that we can extract from these peaks and these slopes, we can see that particularly the Lewy body dementia group, they show that the center frequency, the peak frequency of the alpha rhythm is reduced compared to all the groups that we have seen here. This is at the group levels. And it's the same if we look at the source space. Before we were looking at the sensor space, and now we can see it at the source space. But in addition to this oscillatory change that we do know that exists in Lewy body dementia, we have observed these aperiodic abnormalities that are robust both in sensor and source space as well. So they have a smaller, reduced alpha rhythm. The frequency of the alpha rhythm is reduced, but the non-rhythmic part seems to be more pronounced in this group. And here, when you start comparing all the groups, we can realize that both the center frequency, the dominant frequency of the Lewy body dementia group, are the most sensitive. Here are the results after adjusting for age, and here just by taking the EEG metric itself for the classification of the disease. And you can see that most of the time it's the Lewy body dementias, the one that shows the better performance in classification. But importantly, most of these guys participants are being classified not only based on the positive aspects of the EEG, but on the negative aspects of the EEG. I would say in here that most of our cases, if they have an abnormal EEG, then we can have certain idea that the participant can have dementia with Lewy bodies. But if they have a normal EEG, we are almost certain that they are not having Lewy body dementias. And the same results happen for the aperiodic part of the EEG. So basically, we can say overall that we can mitigate the effects on the side effects on the EEG when we pull data from different parts. But we can say that in Lewy body dementias, it's clear that we can see that there's a steeper aperiodic activity, a pronounced frequency shifting. But in other groups, for example, Alzheimer's disease, these changes are showing only small effect sizes. But at the group level, my take-home message is that EEG can be used more as a screening tool for ruling out neurodegenerative disorders rather than for including and differentiating each specific clinical phenotype of neurodegeneration. And this is important because probably we'll need multimodal data to get better classifications to rule in participants. And yes, the second thing is that the abnormalities that we have seen in sensor space are also consistent in source space, and probably we can stick to the sensor space so we don't need to spend a lot of computational time for diagnosis purposes. We do have a lot of limitations that I hope to address for the next ADPD meeting, and hope you can see it next time. For example, the use of normative models that I know that we are going to discuss in a while, or covariance-based methods. I think we have 1.5 minutes for questions. Is there any question?
You mentioned it's cross-sectional. Do you know how these change within individuals over time?
Yeah, that's one of the issues that we do have now. In terms of the test-retest reliability of the metrics that we are looking at, they have been shown to be consistent in other cohorts, but as I'm basically recycling data from all over the world, I cannot always have longitudinal follow-up. In those cases that I have longitudinal follow-up, I have checked that, and they seem to show good interclass good test-retest reliability. So they are repeatable in terms of...
As opposed to like progression, where the signal might change as a patient declines?
It depends, because most of our cases are in dementia.
Yeah.
So I haven't looked at the MCI so you can see the full trajectory, but in the dementia cases, it's just those features are not that variable. So it seems that they get a plateau, and after that, they're stable.
That would be interesting to see. Thank you.
Thank you so much for your presentation. And so, can you explain me the kind of the pathological and kind of underpinning the change in alpha rhythm, or why it's like the one in LBD differ from the one in AD?
Considering that I only have 3 seconds, I will invite you to look at my GitHub page and look in there, recent publication from last year, where do you have a review on that, on spectral changes of the EEG in Lewy body dementias.